So, hello everybody, welcome back. There has been a speaker switch, so Dimitri is here to tell us about the static analysis of Python. Thank you.
Yeah, thanks everyone for coming here. My name is Dmitry Jemerov, and I'm the CTO of JetBrains and the lead developer of PyCharm. So Andrey has asked me to take over the presentation, so I'll do it myself. So for those of you who are not familiar with PyCharm, it's an IDE that we make at JetBrains. It's an IDE for Python with support for many specific frameworks such as Django and Flask and Google App Engine, with full support for web development technologies, JavaScript, CSS, HTML, essentially all the stack that is there. So PyCharm is actually a commercial product, but we give free licenses for use in education, and we also have free licenses for developers of open source products. We have a booth in the expo hall, so if you have any questions about specifically PyCharm, you can come there, talk to us, and we'll show you stuff and so on. So let's proceed to the meat of my talk. So first of all, what's cool about Python? So Python is a dynamic language, and the dynamic nature of Python allows us to express our ideas with very little code. So we don't have to put in all the declarations of variables that we are going to use, the types that they have, and so on and so forth. And instead we use very concise and short syntax to write the code that we need to write for our task. So you see that Java is quite a bit longer for the same very simple task. Obviously, you don't need to compile your code, which gives you a very fast development cycle, very efficient, and so on. And also the dynamic nature of Python allows you to express like different ideas which would require a lot of code in a statically typed language very concisely by using metaprogramming techniques. So in Python, for example, it's very easy to call a function by building its name from different parts and then simply invoking the function with that name. And in a Java program, this kind of visitor pattern would literally take hundreds or thousands of lines of code if you have a reasonably large hierarchy of classes. And in Python, this single method allows you to build the name of the function dynamically and invoke it as you need it. However, all of this has a downside. So for the productivity that you gain by using all of these expressive powers, you also lose a certain amount of productivity because of the lack of type checks and other static checks. So even though you can write your code quickly, you sometimes have to spend time trying to figure out why the code crashes at runtime or why the test fails, digging through stack traces and trying to understand where exactly the problem is. So for example, you can run into name errors if you make a mistake in a variable name. You can run into attribute errors if you make an error in the name of an attribute that or method that you are trying to call on an object. You can run into type errors if you're trying to combine objects in a way that's not supported by the language. For example, if you want to use extend method to add an item to a list, it will not work because the extend method takes another list. And finally, the import errors are also dynamically checked. So this means that you can run into import errors at runtime if you make a mistake in the name of the module that you are trying to import. And however, for many of those errors, it is possible to detect them statically. For example, if you look at this code, I'm sure that you will see the problem in that code. And if a person can look at this code and see the problem, then probably a computer can also do this as well, while still letting you write in the dynamically typed language. And in fact, there are tools that allow you to do that. And PyCharm is one of those tools, but I'm not only going to be talking about PyCharm. Yeah, I'll mention this later. And with the static analysis tools, you can run them directly in your IDE. So there is still no separate compilation step that you have to go through before you push your code before you can run your code. But immediately as you write your code, you can have your tool inspected at the same time, and you can have it highlight errors for you on the fly. And also in many cases, you also get automatic quick fixes for the errors that the tools support. So with PyCharm has built-in quick fixes, and there are also, for example, if you are using a tool like PyFlakes for your to detect errors. There is a tool called AutoFlakes that will also correct errors for you automatically, and you will please make sure that the errors do not get actually into your running code. And during this talk, we will go a little bit deeper than most talks usually go into looking at how the static analysis tools actually work. So I will not give you a walkthrough of writing your own code analysis tool from scratch, but I will give you through, I'll explain to you what parts are these tools made of and how these parts are combined, and how the existing analyzers like PEP8, PyFlakes, PyLint, and PyCharm's code analysis engine, how they actually work. And I also describe our experience and describe many cases that we have run into which makes it more difficult to write static analysis tools for a dynamically typed language. But in the end, we find that there is a lot of useful stuff that you can do. So, during my presentation, I will show how to write a tool that will find like a number of different errors in this kind of example. So just take a minute to read through this code, and so it's just very simple path manipulation code. Who can see more than 3 errors in this piece of code? Okay, good thing it's not a job interview. Yes, so actually there are 5 errors in this piece of code. There's actually one PEP8 violation, which is very easy to spot, and there is a number of other errors, for example. Yeah, so here they're all highlighted. Who thinks that a static analysis tool can find all of these errors? Sorry?
Not all.
Yes, actually not all, but we'll find most of them.
Attribute error.
Yes, but one of this one will be found. Just as a spoiler. So let's proceed. So first of all, let's look at like the general architecture of like any code analysis tool. So if you want to do to write some tool that processes the code, of course the easiest way is to use regular expressions, just to write some regex that will find something resembling the pattern that you want to avoid having in your code, and then maybe write another regular expression that will replace it with something else. But if you want to write a robust tool that gives a low percentage of false positives, that's not the approach you want to take. Instead of that, you should remember your computer science theory, a little bit of that, and essentially go through this very similar sequence of steps that a compiler goes through. So starting with the lexing, breaking the source code into a stream of tokens, then parsing, building a syntax tree out of this stream of tokens, then resolving names. So if you are using a variable, you need to understand where this variable is defined. Then the type inference, understanding what types the variables actually have. And once you have performed the type inference, you can actually resolve the attributes and check if, for example, if an attribute error is raised by a code access, by some code that you have written. So the lexer is actually a very easy thing to write. So lexer is something that takes the source code and breaks it into a stream of tokens. So it ignores the white space, it ignores the comments directly at this stage, usually. If you care about the white space, for example, if you are writing the PEP8 checker, you will want to keep them in the code, but many lexers just drop all the white space. And it generates this sequence like name, 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 uline, operation, and so on and so forth. And there is a module in the standard library which is called tokenize, which does this for Python code. And actually, the lexer is enough to write one of the most commonly used static analysis tools that Python developers use, which is the PEP8 tool. There was a talk at on PEP8 this morning, and you can watch the recording if you want to learn more about PEP8. And it's actually a very useful tool that makes sure that the code that you write complies to the coding standards accepted in the Python community. And because it's very simple, because it uses just the lexer, just the most basic code analysis form, it's also very fast. and it's very easy to run it on the fly in your editor or in your IDE. And PyCharm augments the page checker with an automatic formatter that can automatically correct the errors and format your code as the page standard says. The next step in the code analysis is parsing. So now that we have a stream of tokens, we can actually build a syntax tree for the program. So in case you have never seen a syntax tree before, this is what the AST module in the Python standard library produces. And you see that for every language contract, there is a specific type of the node in the AST tree. So for example, for an from import statement, there is the import from node. For an assignment, there is this assign node. And the syntax tree has the same hierarchical structure that your program actually has. So if you have classes in your source code, well, it doesn't work that way. So if you have classes and the contents of classes or the functions are nested inside the class in your source code, they will also be nested inside your class in the AST tree. So function definition and another function definition. And at this stage, nothing is being resolved. So the names are just names. So there is this name thing here. We are not trying to understand anything about what this refers to. Is this a parameter? Is this a variable? Is this an imported name? At this stage, we don't care. We just build the tree and we just keep the name as it was used in the source code. Now that we have seen how the AST module in the standard library works, we can actually think if there are other approaches that can be taken. And the PyFlakes and the PyLint modules actually do use the AST module from the standard library. There's the obvious advantage that because this is standard, this is known to work, this is known to be always up to date when the Python language is being changed. And well, if it's enough for you, then it's a great choice. With PyCharm, we do not use any of the standard parsers. Instead, we write our own parser. And one of the main reasons for this is that we have to, in Python, we support all of the Python versions starting from 2.4 and ending with 3.3. And we have the single AST structure for that. And obviously there is no version of Python in which the AST model can parse all of this range of Python versions. And this allows us to write checks that ensure that your code works with a specific range of Python versions that you want it to work with. For example, the new version of Django targets both 2.7 and 3.3 with the same source code base, and using a tool like PyCharm can actually verify that your code indeed does not use any constructs that are not supported by those Python versions, for example. And the second big reason why we use our own parser is error recovery. So when you run a static analysis tool from the command line, it normally sees the code in a complete state. So you have started working on a feature, then you have completed a feature, then you think the code works, and then you run the static analysis tool to verify that it works. Or you run the Python interpreter to actually try to execute it. And PyCharm, on the other hand, normally sees the code in an incomplete state. So in between of writing a function, you have written half of the function, then you invoke the code completion to help you write the rest of the function. And the code completion has to work. It has to be able to understand whatever it was able to parse, and to provide completion variance from the piece of the code that is not completely valid. And this error recovery is something that most normal parsers are not very good at, and it's something that we can have work much better if we have a custom parser. Okay, so now that we have the basics there, now that we have a lecture on the parser, let's look at how we can detect name errors in the source code. So in order to detect name errors, we need to actually resolve names to their definitions. Now this is a bit confusing because the name of the thing which I'm going to show is name, but I hope you can figure it out. So when we want to resolve something, we want to see, we actually go through the list of scopes in which names can be defined and try to find the name in each of those scopes. So the innermost scope in this case is the function itself. So we check if the name is defined within the function, and it is not defined. Then we look at the module, we look at the class level. There is nothing in the class scope in this case. Then we look at the module level, and there is also no definition for name. And the last place that we have to look to is the built-in functions, the built-ins module. And in this case, built-ins module does not define this either. So the object name that would have been defined and the name, this thing here, they do not exist anywhere. So both of these are actually errors, and both of these can be found by a static analysis tool such as PyFlakes or PyCharm. Now, of course, when everything works, so for example, this self is easy to resolve to this self. And actually on the next slide, we'll see how this works. So we have this name node, for example, this one. And the stat name is defined by the import statement. At this point, we don't actually know what this points to, whether it's a function or if it's a class or it's something else. But we don't care at this stage. We just see that the name is defined and the name will be resolved at runtime. Now this is how the name of a parameter is resolved, how the name of an attribute, how the name of local variable is resolved, and and then there are two more names that are not resolved, which will be highlighted as errors. And actually, this kind of analysis is the key focus of the PyFlakes tool. So it detects two things. It detects names that are unresolved and also names that are declared but unused. So if you have an unused function or if you have an unused parameter or local variable, it can highlight those as errors or as potential problems. Again, it's very fast. It does a simple analysis which is possible to do very efficiently, but it does not go very deep. So it does not try to find out, for example, attribute or errors or anything else. It just looks at the single file and makes sure that all the definitions are correct. And again, because it's fast, it's easy to run on the fly in your editor. Now, of course, even with this kind of simple analysis, there are ways to get things wrong. Because Python is a dynamic language, it allows you it gives you quite a few ways to manipulate both local and global namespaces. You can dig into the globals dictionary. You can dig into stack frames and manipulate them. You can use eval or exec, or for example, you can just go modify the dictionary of the built-ins module. And the standard library module getText actually does exactly that. So if you call gettext.install, it will actually go and put the underscore name, this thing, into the dictionary of built-ins. And even though you never declare this underscore name explicitly in your code, it will be defined and will be not an error at runtime. And in order to cope with that, PyCharm and other tools provide a number of solutions. So for example, all the tools allow you to suppress specific inspection warnings. So you can say that at this line, please do not report this kind of warning. And you can use that. In the case of the underscore method usage, you would probably not want to do that because you use this everywhere in your program if you use internationalization. And so you need a different solution, and other solutions are also available. So for example, you can mark this specific name as always defined. So underscore always exists somewhere. We don't care where it is, but it is somewhere. And this actually solves the problem in most cases. Now let's look at other kinds of errors that we can detect. Let's look at how we deal with import statements. So resolving imports actually means two things. So first of all, we need to find the actual module that we import, and the second, we need to find the name that is declared, check if a name is declared in this module. So in order to find the modules, we actually have to know the sys.path that is going to exist at runtime. And like the easiest thing to do this is simply to run the Python interpreter, like the real one or the virtual one, ask it to report its system.path and store this and use it for code analysis later on. The next thing that we do is we actually parse the imported modules. So we actually run the parser to find out what names they declare, look at the under all variable if it's defined there, and so on. And if the module imports another module, then we just go recursively, do the same thing that the Python interpreter does at runtime, simply go down the import chain and see how this is all defined. And obviously things become more difficult when you use imports from something import star, because we actually don't know whether we don't know whether we need to look at this module, or if you don't need to look at this module to resolve the name. So using import star actually makes all analysis tools a little bit slower. But that's not very significant. Obviously, the problem is with binary modules. So for example, if you want to import something from the sys module, there is no sys.py code in the Python standard library. And in order to handle that, we actually have a special tool in PyCharm that imports any module, no matter whether it's written in Python or whether it's binary, and actually reconstructs the structure of declarations in that module. So we actually look at the dictionary of the module after we have imported it, and we see what classes it contains, what functions or attributes are defined on those classes, and we reconstruct the structure of declarations. So we just generate class something, function, and for all the bodies we put in pass statements because we are not able to disassemble the code or reconstruct the implementation any other way. And we use those, we generate them just once, and we use them for code insight later using our regular Python parsing. Yeah, and we call those files skeletons. This is actually a fairly robust solution, and it allows us to solve the binary modules problem in a nice way. Now, of course, the running Python application can modify its own sys path. So just go and append some other paths to it. I don't know, Django does that, for example. And in order to handle that, we allow the user to specify how exactly the sys path is going to look at runtime. So the user can go into the settings of the IDE or can configure the static analysis tool to tell it how the sys path is going to be modified. And this allows us to handle this. Now, a more interesting problem is that the Python import system is actually very flexible and allows a huge amount of customization. And particularly the work that Brett Cannon has been doing recently makes this even more flexible. And in Python 3.3.2. And for example, the Flask library does that. So the Flask library has this mechanism for writing extensions. So when you import something from flask.ext, it does not actually look at flask.ext. It creates a module named flask underscore, and then the name of the extension that you are trying to import, and loads this file. And in order to support that in a nice way, we have to put special logic into PyCharm that will make it possible to understand that. And in the case of PyCharm, the Flask plugin is actually open source. It's on our GitHub. You can look at how this is implemented. And we actually recognize this pattern, and we redirect the imports to the correct place. Now, of course, if you're using the problem with those kind of extensions is that they are specific to each tool, and you cannot easily reuse them between, for example, PyLint and PyCharm. And but when you are using a tool that does support the framework that you are using, it gives for a very nice experience. Now let's look at the hardest part of what we are trying to do, which is detecting unresolved attribute errors. Now let's look at this example again. So we have fixed most of the errors that I have mentioned before. So the self is back here, self.name. OSPath.join is now referenced correctly. And something else. Yeah, the pepate error is fixed. And now only the two attribute errors remain. So we are trying to access the not existing attribute file name on the path object, and we are trying to access the not existing status attribute. So let's see how we are able to cope with those. So in order to be able to see whether an attribute is defined or not, for example, the status attribute, we need to know the type of the things to the left of the dot. So we need to know what these files out of files bracket 0, what this thing actually is, what type it has. And in a language like Java, the type is simply written in the code explicitly. In Python, it's not, and we have to give a fairly deep look at the code to understand what is actually there. The most obvious source of the type information is simply literals or constructors. So if you have like s equals foo equals hello in your code, it does not take a very deep analysis to understand that this is a string, and that all the string methods would be available on it, and all the methods that are not available on string would be attribute errors. Also, when you create an instance of a class, for example, if you create a my class, it's also very easy to know that what this is and what attributes this thing has. The next very useful source of type information is the runtime type checks pattern. So this is fairly widespread in Python code. We have seen it, like many libraries use that, and the people try to make sure that the libraries are used correctly, and they write explicit checks. So if the instance of the parameter I'm being passed is what I expect, then it's all good. Otherwise, throw a type error or something else. And this gives a better diagnostics for users of the library because they know what they are doing wrong immediately as they are doing it. And it's also very good for IDEs. And because or IDEs or static analysis tools, Pylint does that as well, we can recognize this and use this as a source of information about the types. If the code at runtime ensures that this variable has the correct type, then we can rely on this information and we can highlight attempts to access attributes that are not defined on this type as errors. Which is very nice. And if you are not using this pattern, please use it more. It helps everyone, your users of your libraries, IDEs, and so on. Okay, so another thing that we do is we actually support analyzing the control flow inside the function to understand what type a variable can take on different execution paths. In this example, we have a function that can, depending on the value of the argument, it can return either a float or it can return a string. And if we are calling this function, we have to, so in this case we know the type, but if you don't know the type, we have to deal with the fact that it can have a value of one of multiple types. And this is something that we are calling a union type. Like a combination of two types, and trying to access members that are defined on both of those types would be valid. And actually the type system that we have to build in order for the code analysis tool to work efficiently is quite a bit more complicated than the type system of Python itself. So obviously there are simple types, like there are ints and lists and classes in Python, and obviously the same things have to exist in our tools. We have this union type concept that I have mentioned before. So a function can return string or integer or a list, or a parameter can be either a single value of a specific type or a list of values of those type. This is all supported. The next thing is parameterized types. It's essentially an equivalent of Java or C# generics. And in order to provide good code analysis, we have to support this in our type system as well. So we have a list of integers, or you have a dictionary for which we know both the key type and the value type because they can be different. And finally, there are tuple types. So while a list usually has all the values of the same type, and if it has values of the different types, that we just ignore this and don't try to do anything smart about it. For a tuple, it's very important to know the types of each of the elements in the tuple. So for example, if a function returns a tuple of two ints and a string, we recognize that, and we know what it returns, and we provide error checks accordingly. So let's look at how this works in the case of this particular example. So we need to understand what files of zero.status is. So this comes from the all files call. And the all files function is a generator. So it has a yield statement inside it. So it means that what it returns is a generator of something. Is a generator of something. A generator is just an instance of iterable. So in effect, it returns an iterable of something. And because the only thing that it yields is a path object, and we know that it's not just an iterable, it's an iterable of path. The next thing that we do is we store this in a list. And we can also trace that, and we know that a list, we get the list of the same of elements of the same type that the elements that we have put into them. So since we are putting in an iterable of paths, we get back a list of paths. And finally, we take the 0th element out of it, and this element is going to be a path because we know that this is a list of paths. And because of that, it is possible to statically detect that this is an invalid attribute access, because the path object does not define the status method, it defines the stat method instead. So PyCharm is capable of doing this, and I think Pylint is also capable of finding this error, but I'm not 100% sure. Now, how do we actually understand those things about lists and stuff like that? The thing is that we actually have a database of types, parameters, and return values for the Python standard library. right now we use the standard Sphinx and EuroPyDoc format for expressing this information. So essentially what we do is we write our own doc strings for standard library methods, and we put in the type and return type information there, and we use our own DSL for expressing what those types actually are. So in this case it's iterable of t, and t is essentially the type parameter for this thing. And a list it becomes a list of t. And beyond so for the standard library we can build up the information ourselves. Obviously there is no chance for us to build this information for all the third-party libraries that exist in the community. And because of that, we love when people write Sphinx or EuroPyDoc doc strings for their libraries. These kind of doc strings formats have a very good way to express information about types, both parameters and return values, and we rely on this information when it's available. Another possibility to put types in your Python program is using the annotations that were added to Python 3. Unfortunately, I haven't seen anyone ever do that, which is a shame, I think, but maybe annotation will find their use sometime. Maybe it's not going to be used for type, maybe it's going to be for something else, but for now it's not really used much. And finally, what we can do is we can write analysis for specific frameworks. We can write analysis for Django, for Flask, for NumPy that understand the kind of metaprogramming that those libraries do, and that will provide type information for different attributes and functions in those frameworks. By the way, there are also Django specific. There are at least two. I think there are at least two tools which are called Django Lint, which perform different kinds of Django specific checks. So it's not only PyCharm that does Django specific stuff. There are also specific tools for that kind of thing. Now, obviously, there is a ton of ways where when people can do tricky things with overriding attribute access. So, for example, someone can just define getAttr and just accept any attribute reference on their class. And in that case, like for example, this code, this would be valid, but the foo attribute does not resolve to anything specific, and so the tool will need to understand that it's not an error. And most tools actually ignore attribute accesses on all classes that customize getAttr. So once you have something in your getAttr, then we don't know what it's going to do, and we just don't highlight anything as an error. We hope that it all will work out at runtime. A more tricky thing to do is defining attributes outside of classes. So you can so there is simply a function that puts some value on a class. No matter, we don't know why, we don't know what for, but there is a code that puts in there, and there's some other code that references this value. And when we look at this code, we don't really have a good way of knowing that this code exists and that this code applies to this specific instance of an object. So in some cases we would be able to handle that, but right now in most cases we simply highlight this as an error, as a false positive, and you have to suppress this, or you in some way. So you can ignore all accesses to the bar value, or you can ignore the unresolved attribute definition in this particular location. The biggest problem that we run into is actually very simple. It's parameter types. So in this case we have a function that takes an argument of type path, and we have no idea what this is. There is no docstring, there is no type assertion, there is really no context that allows you to understand what this is. So the only clue that we have is the name. So there is a path, and there is a path class, and we can guess that maybe if it's a path variable that it's we can guess that maybe it's a value of the type path. But this guess is actually too weak to use for error highlighting. So we actually use this for code completion, but for error highlighting this is not good enough information for us to think that this success would be invalid. And as a result, this is actually the only error that is not going to be discovered by by the existing static analysis tools in this example. Obviously, there are always more challenges that we can run into. So binary modules are problematic because we have because if the code is written in C, we have no chance of going in there and analyzing what values it can return or something like that. Also, we are actually very much limited by performance. So in PyCharm we want to run our inspections in real time. So we actually cannot run like whole inter-procedural analysis of your code. Instead of that, we have to cut off our analysis very soon so that we can complete in a reasonable time. Tools like PyLint do not face this problem. They are designed to run on a continuous integration server or from a command line, and they can do deeper analysis, and they can look more, like understand more things about your code and be more precise in producing errors. So yeah, that's a trade-off that you have to face between getting errors at real time and getting more deep and like realistic errors. So in the end result, if you look at our example, we have actually successfully found 4 of the 5 real errors and also 1 PEP8 error that is already fixed in this example. So I think that's a fairly good result, and it shows that even for a dynamic language, static analysis tools can deliver a lot of value in your work. So let's look back at the tools that we have looked through. So the PEP8 tool is the simplest and the fastest of them. It does very limited amount of things, but the things that it does, they are very useful, and there is like very low chance of getting false positive errors. And if you care about PEP8, then it will tell you when your code does follow PEP8 and when it doesn't. And it's very easy to run it on the fly in your editor. PyFlakes goes one step beyond that. It looks at unresolved and unused local names. It also runs on the fly. It also runs in editors. You can run it in Vim or Sublime or whatever you want to use. And the errors it detects are also fairly common and also very easy to detect reliably. So there is like just a limited set of tricky things where it gives false positives, but in general it's very reliable and very useful. PyCharm itself has like a very wide range of inspection. There is a lot of stuff that is specific to particular patterns that we do not recommend using, or patterns that violate different style guides that PyCharm is capable of detecting. All of this knowledge in PyCharm is not just used for static analysis. It's also used for code completion, for navigation, for resolving definitions, and for refactorings, like rename also builds on top of that, and so on and so forth. And finally, PyLint, which also supports a fairly wide range of inspections. There is some amount of stuff that PyLint does that PyCharm does not do at the moment, which probably is going to be all covered in future versions of PyCharm. There is quite a lot of stuff that PyCharm does that other tools do not really do. Yeah, and PyLint is actually designed for batch mode execution. It's too slow to run in real time, usually, and it's mostly designed to run on your continuous integration server or in like a specific script that you run when you want to make sure that your code does not have any errors, like pre-submit step or something like that. So just to summarize, use tools. Tools will save you time, and there is a wide range of tools that you can choose to make sure that they work well with your code style. And you can also develop or extend your own tools. So for example, for this problem of having pdb.setTrace in your production code and breaking everything, it's easy to write a tool that will detect that and will not let someone check in code like that to the version control system. And finally, there is a mailing list that was recently created for discussion of code quality tools for PEP8, PyLint, PyFlakes. The PyCharm team is also reading the list, and so you can just go there and discuss the problems that you run into and how you want to use static analysis tools and what you want them to do. And now we have time for questions.
Two questions. First one, can you define also this union type in Sphinx doc strings? I don't use them normally.
I think so. There is a syntax that PyCharm will parse as a union type. It's not like a common. So there is no standard for how you express types in Sphinx doc strings. Okay. But so there's the syntax that PyCharm understands, but it's not really accepted by in the industry.
Shouldn't it be a lint error if you return a string or a number, because it seems like a stupid idea. If you return none or something, then maybe, but.
Well, that's your call. It's possible to write an inspection that will complain about that, but there are like really valid use cases for that kind of thing.
Another thing, is there a way maybe to not just do static analysis, but also actually try to import things and do some runtime analysis, or that's maybe sandboxing an interpreter to avoid any changes? Is it?
Well, it is possible. Well, PyCharm does not do that. PyCharm does not really execute the code in the project. It's an approach that can be investigated, but it's not something that we actually do. Maybe some other tools do that.
Thanks.
Thank you for the talk. I'm not so happy about the recommendation to use more isInstance. That sounds like a Java or C++ or net C-sharpism. Because my thought of Pythonic is, if you want to use a method on an object, use has attribute this method and then do it. So it should be enough if something is iterable, it doesn't need to be a list. Do you think there is an option to parse something like is iterable?
Yes, actually I should have mentioned that. So we actually do understand the ABCs defined in the collections module, for example, and you can check for iterable, and PyCharm will also recognize the check for iterable. If you do has-attr, it's less useful because we cannot really extract much value out of that. But if it's what your code needs, then you can use that, of course. And
can you understand the attributes of objects getted from ORM, Django, or SQL Alchemy?
This is something that needs to be supported for each specific framework. We do support this for Django ORM, we do support this for SQL Alchemy in PyCharm 3, we support this for App Engine, but if you use any, for example, I know Elixir or some other SQL framework, then we will not really understand that.
And what about documenting, for example, return value of function if this function doesn't have docstring, but you want to PyCharm analyze the return value and, for example, provide auto-completion. So is there any mechanism for this?
There will be a mechanism in PyCharm 3. So this thing that I was showing for standard library annotations, you will also be able to do this for third-party libraries. So essentially you will be able to write your own doc strings, which has only the type information, and you will be able to specify that this thing returns this type, for example, for a library that you are using.
Thanks.
Any more question around?
Yeah, there is one over there.
Oh, there is one to the front. Just a moment. Quite far away. Could you pass the microphone, please?
Well, I also have a question.
Okay, like you.
Okay, you mentioned that you have a problem with parameters of the methods, like if there are no assertions that you can use, but you could probably look around the code and find an invocation of this method and infer something from there. Do you think this could work?
This is a little bit of a chicken and egg problem, because we have no guarantee that someone that is using the library that is trying to call this method, that they are doing this correctly. So yes, we could look at that, but the primary problem is that of correctness, and the second problem is performance. So it's kind of expensive to look for calls for a particular method, and it's difficult to do this at real time. But yeah, some value can be extracted out of that.
Just a moment. There are many from that side of the room that I think I did not take a look.
So I haven't used it, but restricted Python, how does restricted Python affect all this? I think PyPy uses it to, because it's easier for them to use. Does that make any static analysis easier, or have you not looked at that yet?
Well, we haven't really looked at restricted Python much because it's not really applicable to real life. So no one except outside of PyPy project uses that, and like investing in something that will only work for developing PyPy itself does not make much sense to us. But I guess, yes, restricted Python should be much easier to analyze in a static analysis tool than like the full Python.
Yeah, do you use any runtime information from the debugger to improve your analyses?
We do collect runtime information from the debugger, but we do not use this for analysis because we have no idea whether it's exhaustive. So we can record the types that were found during a specific run of tests of your test suite, for example. But we have no way of knowing whether it covers all the cases that are possible, and if you are trying to access an attribute, for example, that there is really no case in which this attribute can exist. So this information is actually used for code completion and for documentation, but not for highlighting errors at the moment.
Okay, just there.
So can you run some analysis on tests to figure it out? Because tests should be correct. So you could figure it out from the tests. What is the accepted value?
This might be a possibility. We don't have any distinction between test code and production code at the moment in our analysis.
Oh, more questions?
Hi, you mentioned that you use your own parser because you want to catch a specific case where the code is not already written. I would maybe it's out of the scope of the talk, but what can you say about what you do to just avoid things like having syntax errors because the user is just typing and things are not complete, like missing parentheses or something?
There will be a syntax error at the exact place. So ideally, if we do our job well, there will be a syntax error at the exact place where the user has an incomplete parenthesis or something. But all the code after that should be parsed correctly. And you should have, like, for example, if you have a function definition that goes below that, it should be a function definition at the correct place, correct nesting level, and so on. And the name should be available in code completion and so on.
More questions around?
It works pretty well, actually. Not in all cases, but good enough.
So you mentioned what you use your specific parser also because you try to support different versions of Python.
Mm-hmm.
So could you expand a little bit on how do you let's say try to select which version to focus, or let's say if the code is trying to cover multiple versions, right? So how you would work with that? Let's say there is a couple of features which are, let's say, new in 2.7 and they are recommended to use, and PyCharm would provide a hint, well, you should use that. But what if instead I'm, let's say, targeting 2.6? Well, okay, we are still very old.
So we have this code compatibility inspection, and in the settings you can specify the range of Python versions that you want to be compatible with. So for example, you can say that you are targeting 2.6 and, I don't know, 2.7 to 2.5, for example. And even though you are running the code with the 2.7 interpreter, it will actually highlight all attempts to use APIs that are not available in 2.5.
Ah, cool. So,
Hi, do you have any stats on the most common non-obvious errors, like you find?
Stats, not really. So, no, we collect some stats, but like we do not collect any user code, so it's difficult for us to like understand what patterns actually there are there.
Does the IDE highlight differently the bits it thinks it understands really well and the bits it has no clue about?
Sorry, could you please repeat? I didn't hear you quite well.
Yeah, so does the IDE highlight differently the bits of the code it thinks it understands really well and the bits it has no clue about? As in, can you see like which parts of the code the IDE thinks are definitely correct and the bits where it has no clue if this attribute is valid or not?
So not really. So well, we actually do something like that for some other languages like Groovy in IntelliJ IDEA. For Python, we do not do this at the moment. So we simply, if the attribute that is not that is resolved correctly is highlighted the same as the attribute for which we have no idea whether it's resolved or not. If it's unresolved, we use like different highlighting levels depending on whether it's unqualified or qualified. So if it's an unqualified name, we highlight it as red, and if it's a qualified, we highlight it as yellow, like as a warning, because there might be like more cases when this is actually valid.
Okay, more questions? No? Okay, then
Thanks everyone, and
thank you very much.